So now let us step back and see if we have the theoretical tools built within the de Broglie hypothesis to begin to explain these discrete spectra. So our new topic is then see if we can do this. See if we can get the discrete spectra, or I really should say the discrete energy levels, from information that's buried within our de Broglie hypothesis. And then what this is going to lead us to then is a procedure known as the Bohr Sommerfeld quantization. So let's see if we can kind of walk ourselves mentally through the key components in the de Broglie hypothesis that might be able to explain the existence of these discrete energies. So it seems, right, that systems, mechanical systems such as the ones we've been studying, quantum mechanical systems seem to have certain very preferred energy values. I mean, they're so preferred we never see things that don't obey this. The systems have very preferred energy values or energy levels. And I should say that they are discrete. And being discrete then, I will write them E with some kind of countable index n, right? So n, again, could be, 1, 2, 3, something like this. So systems have very preferred discrete energy levels. Now, we have to think, what does this correspond to in the de Broglie hypothesis? Now remember, the de Broglie hypothesis basically tells us that for a given particle, we can describe its probability distribution as a superposition of waves of certain wavelengths and certain frequencies. Now, so we have to think then, how do superpositions of waves behave? And you have a lot of experience with those from your earlier physics classes. So if I build up a superposition of waves, have I ever seen a situation where there's certain something that would correspond then to certain preferred energies in quantum mechanics, but maps onto something else maybe that I've seen in the theory of waves? We want to ponder that a little bit. What gives us certain very discrete, very preferred wave behavior? Now, let's walk down a little bit through the de Broglie hypothesis to make this connection. Well, as you know, the numerical values for these energies we would be observing for mechanical systems correspond numerically to values of the Hamiltonian of the system. Right? The Hamiltonian of the system is numerically equal to the energy, at least for systems we are looking at now, these mechanical systems without magnetic fields or something very exotic. Later on, we'll learn that what I'm saying really you should all phrase in terms of the Hamiltonian. But for now, this observation of these discrete energy levels tells us that the numerical values of the Hamiltonian for our system are, in fact, discrete and can be labeled in the same sort of a way. And now, using the de Broglie hypothesis, we know that those discrete, very preferred values for the Hamiltonian correspond in turn to very discrete preferred values of frequencies in the superpositions of waves describing my particles. So these frequencies then also must be coming into discrete values. Now that should remind us something of something very familiar from wave theory, right? For waves, for superpositions of waves, right? We do see strongly preferred frequencies. And that comes from the phenomena of resonance. And here is how resonance would look for a classic wave system. The classic example of such a thing is waves on a string. And you guys know how to do this. If I could have two fixed walls, I string my string across the walls, and then I can, tickle or stimulate this string in various waves. You guys may have done this in a lab where you just put a little pin that pushes at different frequencies on this side, or more frequently that's done in the middle. And then what you would find as you do that is most of the time you don't get anything really on this string. You usually get a very low amplitude. But every once in a while, if you do this at just the right frequency, you build up a very large response in the form of a standing wave, where in the standing wave, all of the particles in that wave just move up and down with exactly that same frequency. So you're going to have this kind of a motion, right, on the wave, everybody moving up and down with a very strong response occurring only at these certain very preferred frequencies. Now, that seems like a promising connection, because a strong response, which would mean a strong amplitude in a superposition of waves, corresponds in quantum mechanics to a very high probability. So what we're saying is the very high probabilities occur when the frequencies match certain very preferred values, which would then say it's very high probability we only observe certain very preferred energies. Likewise, if you are thinking about a frequency that doesn't match one of these resonances, you get a very low amplitude, which in quantum mechanics would correspond then to very low probability. So we don't expect to see energies in between these preferred resonances. Now, we can be a little more rigorous on that, and we will in just a moment. Now, but first I just want to remind you a little bit about how this wave idea works. You'll notice, right, that there are certain very preferred wavelengths, and given the dispersion relation, I can connect those wavelengths and the size of my string directly to those resonance frequencies. That's how we usually determine them. Now, the reason for that connection is as follows. I'll try to sketch it. It's kind of hard to make the sketch come out just perfectly. But the idea is, suppose instead of this, perfectly sized half wave in here, I have something that has a little bit longer of a wavelength. I try to put in, let me try to draw this again. I try to put in something whose wavelength is a little too long, right? So now you recall what happens when, if I have a wave like this and I'm sending it in to this hard wall, there's going to be a reflection, which is good in a way because this thing was about to head downwards, but when it reflects, it inverts the wave. So I'm going to be starting up here, and I'm now going to have my half wavelength traveling back. So it's going to do something like this, but again, its wavelength is too short, so it's going to once again miss its target over here. It again gets inverted in its reflection and begins its travel back, right? And I'm getting something, well, I made that a little too short wavelength, but hopefully you're getting the idea that as this happens, what goes on is I'm getting this superposition of these waves here, all coming in with the peak at different locations. And so, again, as I said, this gets hard to draw, but I'm getting all these different phase values adding together on these waves. So the total superposition of these at any location is basically they'll always cancel out because I'm always getting all kinds of positive values and negative values. And as they add together, eventually I get 0, which in our quantum picture would say there's no probability of this happening. So there's a special criterion we need, which is that to describe what these preferred wavelengths are. So the criterion that we use is what we want is that the full path length, and by the full length, what I mean is for a complete cycle, right? Because the wave travels across, is reflected, travels back, and then gets reflected once again. And when it comes back to that reflected once again, I want it to be in phase with the original wave. So that means this full path length has to be in phase with the original wave. That means that length should equal n, some integer, times lambda, some integer number of wavelengths. Now, for the classic wave case, if my string has length L, what that analysis is telling me is that I want 2L to equal n times lambda. And that then tells me where n is some, again, integer number of wavelengths, so I should say n equals 1, 2, etc. So then lambda takes on the value of 2L over n, and that would be lambda sub n, I would say, because there's a discrete set of these preferred lambdas, and those, of course, will ultimately give us a discrete set of preferred frequencies. But what I really want to emphasize here is that this condition really does give me the correct wavelength. You'll notice the lowest mode in this system has just half a wave in it. That has a wavelength of 2L, which is why I'm only seeing half of the wave in my distance L, and this kind of argument reproduces that perfectly. So we want to use a very similar criterion because the mathematics is all the same in quantum mechanics. It's just that the interpretations are different, where now the frequencies are telling us about the energies of the system. The wavelengths are, of course, related to the momenta. And finally, the amplitudes that you get out, whether they are small or big, are, of course, directly related to the probabilities. But let's build up this criterion and state it mathematically into the Bohr Sommerfeld quantization condition. So the Bohr Sommerfeld, this is what you want to impose to get your quantization. So Bohr Sommerfeld, otherwise known as BS, quantization condition. So what we are saying is just that if we go a full cycle, right, back and forth, right, for the full path length, so that means I'm going to do express it as some kind of an integral, and this is for a full cycle, right? I'm integrating then, I'm going to integrate it this way. ds will be my distance, or I'll divide the system into a bunch of tiny little lengths, and then I want to divide length by length per wave. And the length per wave is the wavelength. And the reason why I do it this way is then this cancels nicely. Length divided by length per wave means as I'm going around and doing my integral, I'm just counting up how many waves there are, and I want that to be equal to an exact integer. Now, I realize I'm stating this in somewhat of a more formal way, and I'm doing this so that we can analyze a wide variety of systems, and I want to give you the truly formal statement for the Bohr Sommerfeld condition. Now, that all comes from my wave physics. This will give me the criterion for then one of these situations where the waves superpose on each other and then correspond to high probability. Now, to connect the other variables to the de Broglie hypothesis, we recall, of course, that wavelength is just h, Planck's constant, divided by the momentum. So now we have a very nice condition here. Let me just rewrite it a little bit, and we can put a box around it. One thing I'd like to do is to keep the p and the ds together, so the p has to come up on top. So I'm going to have integral over a full cycle of the momentum of my system times the distance that I'm traveling as I go around my full cycle. And this then has to give me the other side of my equation, which has n in it, of course, the integer. And then I want to put my h bar onto the other side, and h bar. So I'll put a box on this because that's the famous Bohr Sommerfeld condition. Now, one reason why I like to write it in this form, and you will learn this as you do more advanced mechanics. You very frequently find in advanced mechanics integrals in this form. Usually they're written as p dq. Usually we use q for the distance in advanced mechanics. But I just want to point out there's some very deep connections here to classical physics as well. But this then is the basic condition that we want to use to analyze systems to determine the criterion for their quantization. And the idea then is you analyze the rest of the motion using classical physics, and you combine it with this condition, and then that is our quantization condition, which hopefully we will see will lead us to meaningful values for these discrete energy levels.